Sorry, I'm making a racket with that. Is that okay at the back? Wonderful, thank you. Right, good afternoon, everybody. Yay, someone's here. I love it, wonderful. Right, mathematics, fantastic. So lovely to see you all here again. Got quite a few notices to go through here, so bear with me, a little bit of housekeeping to do. But just before we go through all of that, just an extra one from yesterday. Oh dear, it decided to flicker in and out, hasn't it? Hopefully it'll settle down when I start putting. Okay, so we rushed that at the end yesterday, so I put an extra one up. Well done to those of you giving it a go. Really, I'll always put something up at 10:02, so you've got something that's revision from the day before that will just consolidate and make sure there's no questions left over from previous, all right? So take the chance to do it if you can. Work with your mate if you want to, absolutely fine. But I just want to talk through the strategy and then something that we mentioned yesterday, but let's consolidate about our solutions. So what was the philosophy? What are we going to do? Take it easy in stages, don't rush it. What would be a good philosophy? We want to get rid of those those expressions on the bottom lines because they're getting in the way. So we could start by multiplying through by x plus 2. So here's one I prepared earlier, true Blue Peter style. So bear with me to save me writing it all out again. So I multiplied through by x plus 2, but you must remember that everything gets multiplied by x plus 2. Yes? You can't just multiply one thing on one side of the equation and expect it to balance. So you've got to multiply through all the way. And then I saw what cancelled, so I got down to this line, which is looking a little bit nicer. But I've still got an x minus 4 on the bottom, so what can I do to undo that operation? Multiply through by x minus 4, brilliant, and I must do it to every single term. So I'm multiplying through by x minus 4 all the way through my expression, yes? Then I'm seeing what cancelled, and lo and behold, I've got everything on a single line, which although it looks slightly huge, it looks a lot better than what we had originally. Everybody okay? I'm just collecting like terms. All I'm doing from that point is tidying up and collecting. My x squareds happen to cancel out. My x's work out to give minus 9x, and my numbers work out to be 12 on the other side. So, solving, I got x was minus 2. Did anyone get there? Yay, fantastic, absolutely fantastic. That's as hard as they come. So if you can do those, you're absolutely well on course. But we haven't finished. What haven't we done? Our checks, exactly. So if we put the x is minus 2 into the original expression, remember, what happens? We end up with that 0 on the bottom, which you can't do. So it's not a valid solution because we cannot divide by 0. Yes, so we find a solution and got all excited, but as it turned out, it wasn't a valid solution. How does that sound? Everybody okay? So check your solutions, and that's the reason why, because you think you may have come up with a solution, but it might not actually be a valid one. Is that okay for everybody? Okie doke, right. Bit of housekeeping. Those of us watching remotely, there are quite a few. I'm putting this up for their benefit. If you're watching remotely, there's a little button on there. This was a post that Rosie did, so it's on the Learn site. There's a little button up there. If you want to chat with Rosie and you're on the live stream, you can chat with her away and she'll reply. So those are not for people here because you can chat to me, hopefully, but people, hello out there, wherever you are, watching live can actually ask questions using that little button with Rosie. Okay? Right, next bit of housekeeping. Do we have Solomon here? He's not? He's isolated. Oh, sorry to hear that. That's really sad news. Well, I'm glad we mentioned him. Solomon, you may have had that forum post. I certainly got it at the weekend. He's your class rep. So please do respond to Solomon if he asks you for feedback or if you want to ask any questions that you'd like to put to us, but you don't want to talk to a lecturer directly. Solomon is your person to go through. Now, usually a class this size, we're quite happy to 2 class reps, which is very useful sometimes. Solomon, I believe, is from engineering, so particularly if somebody who's not in the engineering stream wants to be a Math 101 class rep, consider that and come and talk to me or send me your details. All right? Okie dokie. And best wishes to Solomon, wherever if he's watching live. Okay, I've also had lots of questions about what can I do? The pace of the course is quite fast. What can I do? What are your recommendations? So I'm just popping this up. This was feedback from a previous semester. But it's perfectly valid today. They were asked at the end of the course, if you could give yourself one single piece of advice, what would it be? And I want to thank the people out there personally who have reached out, and I've seen lots of you, and you've come to meet me or email me or whatever. It's absolutely fantastic. You're really welcome to do so. So help is there. Please do ask. Don't let a little problem become a major problem. The course is not going to let up. The speed is going to continue. So if you feel you're slipping, don't think, oh, never mind, I'll catch up in study week. It doesn't work that way, okay? And one of the best things I can recommend at the minute, now this is on the Learn site as well. See if we can get it to focus. Online Zoom help. They've been very quiet up to this point. So they're feeling a bit unloved. So could you please join Zoom and reach out to them? Yes? Those are on, it's on the Learn site. I just took a screenshot there of it. There's help available every day bar Wednesday, but if we find we are swamped with people wanting help, easily put on more sessions, not a problem. All right? So please make a note of that. Put it in your diary. It's an extra thing. And it's a very sociable subject, mathematics. It's not an isolation subject at all. It's a very much, let's do it together and bounce ideas of each other, check solutions, check each other's working, talk it through, blah, blah, blah. We're very collaborative beings. So please reach out. It's always nicer doing problems with somebody than doing it on your own. Okay? And my other great piece of advice is, it's wonderful you're here, it's wonderful you're watching lectures, it's wonderful that you're going back over them, making your own notes as you go. But it was fun watching someone else ride a bicycle, but you never really find out what it was all about till you fell off a few times. So let's come and fall off lots and lots and lots of times, and then we'll eliminate all those errors that creep in along the way. All right, any questions, shout out, let me know. All good? Right, today, I believe we're looking at trigonometry. How many people feel comfortable with trigonometry? Surprisingly few. I don't know how much they do at school these days. Yay, I'm glad the back's looking good on trigonometry, which is excellent. Why do we need to do trigonometry? A lot of our modern world would fall apart if we didn't have trigonometry. It's in every discipline, it's used in all sorts of things, so whatever you're going to do, you will need to have a basic understanding of trigonometry. If you go on to engineering, you will need a very deep understanding of trigonometry. So let's make a start today, and then we can come back and do more in-depth stuff later on. All right. Let's see if we can get the good old pens to work today. Any questions? Trigonometry, what does it mean? Triangles. The what of triangles? Trigonometry. Close measurement of triangles. Yeah, that was a measurement of triangles. Absolutely. Those Greeks knew what they were doing. They were absolutely amazing. So they had this sussed. They really did. So trigonometric functions are useful to model repetitive behaviors. Those periodic functions. Why do we call them periodic functions? Because they tend to repeat in a nice pattern. Yes? You'll see all sorts of things. We usually see it written as something like sine of t or cos of t. Yeah. So it's a function. You'll be doing more on functions later. So to warm up to that, we're going to be looking first at some geometry and triangles. This should be revision for a lot of people, so I'm going to go fairly quickly, shout out as we go if there's anything you want me to go more deeply into. Okay, 360 degrees makes a complete circle. So 180 degrees in a half circle. Yes, everybody okay with that? So we can continue that and make a very wobbly circle. 90-degree angle is called a right angle. Most people are familiar with the little box symbol to indicate a right angle. And angles meeting at a common point add to 180 degrees. So it's obvious that those two add together to get the full 180. Yeah, everybody okay with that? And these two lines, what do we call them when they're at right angles to each other? Perpendicular, fantastic. So we'll talk about perpendicular. Right, I'm whizzing fairly swiftly on. We'll get on to some examples in a minute. So a triangle with one right angle interior angle is called a right angle triangle. Now there's a novelty, right? The three interior angles of a triangle add up to 180. So here we have our right angle. If we call this angle A and this angle B, A plus B must add to 90. They're the other 90, so the whole three make up 180. Fantastic. We're working in degrees at the minute, but we'll soon be swapping to radians because that's the method that we use for lots and lots and lots of things. So three interior angles add up to 180, and the area of a triangle, half times base times height. Remember, it is the vertical height. So it's this height here we're talking about. Okay, so area of any triangle, half times base times height. Right, one very, very useful thing about triangles, we call them similar triangles because they're in proportion. So you can think of it as a triangle that you've just put on the photocopier and you've blown up. Yeah, so it's a giant copy of the little one. Yes, so the ratios of the lengths and angles stay the same, but it's just been stretched in proportion. Does that make sense? So we call them similar triangles because their corresponding angles are equal and the ratios of their corresponding sides are equal. So what do we mean? Corresponding angles are equal. So angles at A, this is our little triangle here, and this is our big triangle. So what angle in the big triangle is equivalent to angle A? D. Yeah, so bless you. And similarly, angles at B and E are the same. And angles C and F are the same. Yeah. So all you're doing is you're stretching it, keeping all the proportions constant. Yeah. So the handy thing is this means the ratios of their sides are equal as well. So what do we mean by that? So if we had side AB, and we did a ratios just a fancy fraction, yes? So if we divide by, say, we do BC, that will be equal to the corresponding ratio of the big triangle. So what's the corresponding ratio of the big triangle? Is he right? Fantastic. Simple as that. And similarly the others. You could probably all think of another pair of sides that are going to do that. So that's the nice thing. So if we know some of the sides, we can find the missing ones. And I reckon that's what's going on the next slide. So we're going fairly quickly. Is everybody okay with the pace at the moment? Yep. I'll get you to some work in a moment. I'll wander around and see if anyone's got any questions. In fact, why don't I do the first one and then you could do the second one? How about that? So find the unknown lengths in the similar triangles. If we didn't know they were similar, we might be in trouble. So they have to be similar triangles, yes, to get that ratio thing going. So let's look at that little triangle to find out what A is. So we know this one and this one on the big triangle, so it would be very useful to pair A up with the 24. So I could say the ratio A over 24 is equal to my 35 over 40. Does that work for everybody? We can simplify that now if we want to. Just divide top and bottom by 5. But if you want to do your simplification later, that's absolutely fine too. So therefore, A would be 7 over 8 times that 24. I make that 21. Yes? Thank you. Keep me right. Everybody okay with that? Please shout out if there's any questions. Have a go at B. I'll catch you up in a minute. Anyone not sure what they're doing, give me a wave and I'll come and see what your ratios are doing. We've got some very happy bunnies today in class. It's lovely. It's nice to see people's eyes smiling behind the masks. Check with your neighbour if you want to. Make sure they're on track. Make sure you get the same answer. So look at the other triangle. Which ratio have you got that might be handy? So I would go for B over 40. The equivalent side on the little triangle, 15 on the top, 24 on the bottom. Yep. But you could have used one of the other ratios. Now we find our missing side A. You can simplify that now if you want to. 3 is the best we can do, isn't it? So B would therefore be multiplying both sides by 40. I make B 25. Thank you. Any questions on that? Similar triangles is one of those things that we put in exam papers and they're not done terribly well, and I don't know why. I would love to know why they don't get completed well in exam questions. So if anyone's got any questions I might be able to help with that, please shout out and let me know. Okay, happy to move on? We're still writing, let me know. Yep. I think we've got another one to do. I might have to draw a triangle here, which is going to be, my wonky lines will come into play. Right, have a read at that and see if you can do yourself a sketch of the new triangle. Schooner. Kind of boat? Sorry, what was the question? I'm missing the point. Can someone help? It's a type of boat, isn't it? That's okay, no, it's fine, absolutely fine. No, sorry, I just didn't understand your question, so please keep the questions coming, really appreciate it. They should just have said triangular sails on a boat, but there you go. I didn't write the notes, sorry. Right, I'm going to attempt to sketch. Yours will be much better than mine. So what we're doing is we're making this 2, so we're adding 2 onto here. Yes? So if I try and draw something that's going to be bigger in that direction, bigger in that direction, and bigger in that direction, while roughly keeping the angles the same. The angles should be exactly the same, but I haven't got a way of doing that on screen. So I'm going to call that one A, I'm going to call that one B, and we know this one is 6 plus 2, we know that's going to be 8. Now we've just blown it up as in a photocopier, so that little angle there equals that little angle there. This angle has to be equal to that angle, and this angle has to be equal to that angle. Is everybody okay giving it a shot? Got to find those two other missing sides. So find A and find B. How are we doing? Anyone got any questions? All good?
Like, just over here, for example, you can actually just go 40 divided by 24 and you'll find like scaling, which is, say, 5/3, and you can just divide the more times them by 5.3.
That's what we're doing. No people see it. That's absolutely fine. As long as you've got your ratios in the right, it's absolutely fine. It's the way you visualize it happening, which is great. Yep, you're just doing a scaling factor as opposed to the, yeah? How's it going? What today? 13.37. I'll check that one. Keep it as an exact value, all right? Any other questions up this side? All good? Right, let's see. Some people have found A already, so let's see what it works out to be. So I used A over 8. Is 9 over 6. So A equals 9 over 6 times 8. $12 meters? Yes? Somebody had a decimal approximation there, but maybe you were going for B instead of A. Find B. So B divided by 8, and then on the other triangle would be 10 over 6. So B is 10 over 6 times 8. You can leave it like that, or you can simplify it, be 40 over 3. Don't introduce a decimal unless it says to give a decimal approximation. Just leave it as an exact value. Anyone not sure about those ratios? Similar triangles. We can do them because we know that they are similar triangles. We're told they have the same internal angles. Yep. Right, any questions? All right, we'll march swiftly on then. And I just need to put a little 2 up there. Your notes have been corrected, but I forgot to correct 9. Right, can we just have a bit of hush, please? Thank you. Pythagoras. Who was Pythagoras? He was a Greek guy who was very keen on triangles. Absolutely. Right. Right angle triangles. Pythagoras' theorem for right angle triangle. If C is the length of the hypotenuse, A and B are the lengths of the other two sides, then A squared plus B squared equals C squared. Which one is the hypotenuse? The one opposite the right angle. The one opposite the right angle, which is the longest side. So in this case, C is the hypotenuse. Okay, so a quick chance to practice. Good old Pythagoras. Give it a shot. I'll come round and see if there's any questions on that side. Everybody okay? Right, as I say, the one on the left, if you know some Pythagorean triplets, you'll recognize that one. That's 25 and 144. $13. The other one, I don't think we get an exact value. This time, am I doing 8 squared plus 5 squared? The hypotenuse is the 8. Careful. Well done. So we could do 5 squared plus b squared is 8 squared. Oh, it's y actually. Sorry, isn't it? Apologies. We've got a label on it there already. That looks healthier, doesn't it? So y squared is 64 minus 25, which is 39. So we're just going to leave it as an exact value. Right, who got there? Yep. Everybody okay about Pythagoras? All right, well done. Right, we can use Pythagoras in all sorts of ways. Have a quick sketch of the next one. Have a quick sketch, plot those 2 points, and we'll see how Pythagoras helps us find the distance between those 2 points. We have a very wonky set of axes here, so we want 1, negative 1. We want 2, 4. So that one's my 2, 4, and that one's my 1, negative 1. And we want to find the distance between them, which we'll call D. Give it a go. See how you go. Can you work out the lengths of the two sides so we can find effectively the hypotenuse? That point is effectively 2 minus 1, isn't it? So the horizontal length is 1, and the vertical is perfect. Well done. So D must be the square root of 26. And I'll pop something under the document camera because that formula effectively is on your formula sheet. Distance between 2 points. So it's effectively Pythagoras. So some people might want to just use the formula from the formula sheet. If you're not into plotting your points and seeing what's going on, the formula will do you just as well. I'll put the formula on the other side so you can see it. Every okay, distance between 2 points, it's effectively Pythagoras theorem. All good. Check out your formula sheet. We're going to be referring to it later in the lecture as well. So it might be handy, print yourself off a copy, keep it for all the stuff we're doing from now on. Right. We've been using degrees. We said there's 360 degrees in a full circle, 90 degrees in a right angle. That's called a right angle. Anything smaller than that is an acute angle. Anything bigger than that, but less than 180, is called an obtuse angle. Anyone know what the next one in the series is? Acute, obtuse, reflex angle? You don't need to know that. And an angle of 180 degrees is just basically a straight line. Right. Right, we're going to move from degrees onto radians. There's loads of reasons for this. One of the most useful things for us in Math 101 is that calculus works on radians. Calculus doesn't work on degrees. So we're going to get used to just working with radians when we're talking about angle measurement. So what is a radian? Radian is basically, if we have 1 radian, it means the radius of the circle is equal to the arc length. Those two, the blue and the red distances, are the same. And if they're the same, the angle is obtained at the center of the circle is 1 radian. So a complete revolution of a circle is 2 pi radians. Everybody happy? Pi is an irrational number, so we won't write it as a decimal approximation. We'll try and leave it as pi where necessary. This is the one I always work on. Pi radians equals 180 degrees. I just find if I remember that, then everything else flows naturally from that. What would our complete circle then be? Because we know that's 360 degrees, that would be 2 pi radians. But if you want to do a scaling factor, and some people like to use that, we'll see that on the next slide. Everybody okay? Checks on both screens. Right, so pi radians is 180. So if we're going from radians to degrees, we would actually multiply by 180 over pi. If we're going from degrees to radians, we would actually multiply by the reciprocal of that, pi over 180. Some people like to do it that way. For the ones that we've got there, we don't need to worry about that, but you can check it out. That's the scaling factor if you're going from one to the other. So let's convert the following angles. So if we know 180 degrees is pi radians, what would 90 degrees be? Yeah, simple as that. And what would 30 degrees be? So it's effectively 180 degrees over 6. So that would be pi over 6 radians. Everybody okay? 30 is a sixth of 180 degrees. So that would be a sixth of pi radians. Yeah. What about pi over 4 radians? Can we go the other way? If pi radians is 180 degrees, what would pi over 4 be? (180 over 4, which is 45 degrees. Perfect. And what would 2/3 be? So remember, if in doubt, pi radians equals 180 degrees. So 2/3 of that would be 2/3 of 180, which is 120 degrees. Get quite comfortable moving between the 30 degrees, the 60 degrees, the 45 degrees, because they're what we call the angles in our special triangles, and we're going to be using the special triangles all the time. So feel very comfortable going between those multiples of 30, 60, 90, 180, because we'll be using that quite a bit. Right, we'll need the formula sheet for the next one, so I'm just getting lined up. I'll try and flip them over so you can see both on, but at the minute I'm just going to put all my trigonometry stuff there at the top of the screen, because we'll need those when we go on to the next example. Right, find the radius of a circle with area 16 square centimeters. Area of a circle on your formula sheet, pi r squared. Okay, so we know in this case our area is 16 is pi r squared. So r squared is 16 over pi. We're going to leave it as a whole. We're not going to do a decimal approximation for pi. So r is the square root of 16 over pi, or you can write that over 4 of the square root of pi if you want. And that would be in centimeters. Any of these, don't worry, you don't have to remember the formulas. They're all on the formula sheet. Let's check that out again. The next one is the area of a sector. Let's have a look at our formula sheet. Area of a sector. Can everyone pick that one up? Area of a sector, a half times r squared times theta where theta is the angle in radians. Yep, so jot down the formula and then we'll use that on our example. Area is a half times r squared times theta. We've got our angle in radians, so we're doing fine. So theta equals pi over 3. Everybody know what we mean by the area of a sector of a circle? If I draw a really, really bad circle, that's terrible. But effectively, that little angle is theta. And we're after this area of that sector that I have drawn there. So from the formula sheet, a half r squared theta. A half r we know, well, r squared we know is 16 over pi, and theta we know is pi over 3. So those pi's are going to cancel out. We'll have 8 on the top and we'll have 3 on the bottom. Units of area. Centimeters squared. Yep, squared units for area. Well done. And the next one we need is the circumference of a circle. So let's check that out with the formula sheet as well. Yep, everybody okay? Circumference of a circle, pi times d, or the 2 pi r because the diameter is twice the radius. Yeah, so pi d or 2 pi r. You've got the pi d one on your formula sheet. We're going fairly quickly. I put the annotated notes up as usual. Come and see me if anything's not clear. So from the formula sheet, pi times d, or in other words, 2 pi times the radius. Remember your angle in radians for all of these. 2 pi, our radius is 8, so that's 16 pi. And that's circumference, so that would be in centimeters too. Just all of these, remember, everything, if you've got an angle in there, has to be in radians. So check your question carefully, make sure that you've done that conversion if you need to. And last but not least, let's have a look at the what was the next one? Arc length, wasn't it? Yeah, arc length. Traditionally called S, r times theta. Theta is your angle. Don't forget it's in radians. Okay, so get familiar with all of these formula on the trigonometry part of your formula sheet. So S equals r times theta. And once again, it's a length, so it'll be in centimeters. Any questions on any of those? Those are just a matter of selecting the right formula from the formula sheet, making sure you're in radians, thinking about your units. If you get a length at the end of it, just think, is it in centimeters or what is it in? Any questions on any of those? Yes.
So you say I usually leave the answer as 16.
You certainly would. That's what I'd expect to do. Leave any of these as exact numbers as soon as you put an approximation for pi, because pi is one of those numbers that goes on and on and on forever, as you know. So anything we do would be an approximation. So usually the question would say leave your answers as exact values. It's a really good question. 16 pi is an exact value. Yeah.
Why do we need to use radian?
Why do we need to use? because the formulas only work on radians, and that's the thing to do with the arc length when the radian's 1 unit. 360 is a very artificial way of measuring angles. 360, I think, Clemency, this is her area of expertise, but I think it came from people as far back as the Babylonians. They watched the skies, and they were thinking about the rotation of the Earth, and 300, they knew it was approximately, as we know, 365 days. So 360 was close enough. So 360 became this arbitrary measurement of a complete circle. And also 360 has the added advantage that think of how many numbers divide into 360. You know, we can see why 90 and 45 and 6, you know, they all go into 360. So 360 is used for a very long time, but a lot of stuff in mathematics will not work if you've got angles in degrees, and we can look at that as we go through some of the examples later. But certainly those of you who've done differentiation, if you're differentiating sine, do you remember what you get? Cos, cosine. That only works if you have it in radians, because otherwise you'd have to have a scaling factor for the 360. So there's loads and loads of reasons, but I really like the question. Have a delve, have an explore, and all the rest of it, because it really is an interesting topic where all these numbers have come from. Any other questions? Really, really good to get your questions. What did I get? Of this circle? Same circle. It's a good thing to look out for. You're absolutely right. I might have been making a giant assumption there, but you're absolutely right. It's this circle. Carefully watch that when you're looking at an exam question, because you've just got to keep your wits about you sometime and make sure you're talking about the same circle. Any other questions? This is brilliant. So these are all on your formula sheet. Become very familiar with it, okay? Because you need to be able to use them quite easily. We're doing more trigonometry tomorrow. I want to set you up with a little question to ponder for homework. So just before you go, this isn't on your notes, so if you want to have a go at it for homework tonight, there is our question. Assume the Earth is a sphere, or else this whole thing falls apart. So assuming the Earth is a sphere, which it's obviously not, it's slightly flattened, just have a go at that. It would be just nice to see it and just see what it works out to be. Thanks ever so much, everybody. I will see you tomorrow.
How would I go about getting some execution in regards to programming code and stuff like that?
You can either flick me a message and come see me work through it, or you can try one of the Zoom sessions. They're sitting there at the other end of Zoom, and you can delve in and out for questions. You don't have to sit in those sessions. So if you've got something quickly you want to ask, go on there, say, I just want to go through one of these with somebody, and they'll be very glad to talk through it. So whatever works for you, absolutely fine.
Thank you.
January 7. It's on the front page of there, and all those photographs that I took. Email and my room number and everything, just under the photographs. Looking it on the learn page. I'm next, there's 3 of us. I'm just in a bit early because we're not here. We should have been teaching this week, so we just got me as an extra instead of my normal students. All right.
That's it, thank you.
See you then.
Bye.
Hello. That's a very good question. Did I make a mistake because it's actually square root of 16 divided by square root of 5, which is 4 divided by square root of 5. have to go back and correct it. 1 second, 1 second. Can't be too far away. No, I did 4 over square root pi.
Oh, yeah.
I did. It was okay. The notes are all right.
Yeah.
Yep, so I square rooted the 16 to give 4 on the top, and I left the bottom
Oh,
one
you
square root.
rooted. Oh, sorry.
Does that make sense? No, thanks for checking. That's awesome.
Okay.
Good. Hi, right, next question. Yeah, go for it. I'm packing up some guys coming in.
So I was just wondering, there was one of the questions there that was how many degrees is 2 pi over 3 radians, and I thought it was 240, but you wrote down 120 and I got a bit confused there.
So 2/3 of 180?
Is 2 pi...
2/3,
I
because
thought-
pi is 180 degrees, so 2/3 of that would be 2/3 of 180.
But if it's 2 pi, is that not the 360 instead?
360 over 3 is 120.
Oh, okay, never mind. I got confused because I saw the 2 over the 3 and thought 2/3.
No, you're good. Thanks for
Okay,
checking.
yeah.
No worries at all. Keep me right, because I can easily write rubbish down here. Just keep me right, okay? Hello.
Last week I didn't go to Com A, and the time is all full. So what should I do?
You need to email Rosie, and she will make sure that you get into something. So email her straight away this afternoon. She is checking emails. Just make sure you get into a class, all right?
Oh, okay.
Do it
Thank
straight
you.
away. You know where her email is, don't you? On the
Yeah.
Learn page. Yeah, cool. Right. See you soon.